Hey everybody, I'm Professor Paul Day. I'm a geologist and environmental scientist, and I'm deeply interested in soils. I hope you're going to enjoy this docu-lecture where we're going to talk about the soils that are all around us and figure out what's going on beneath our feet. Think about it. As human beings, we normally only think about the surface of the earth, about what's going on behind us, these grasses and the trees that we see in the distance here. We don't normally think about what's going on beneath our feet. When we think about soils, we think maybe a couple of inches, maybe a couple of feet. We don't really think about what's going on at depth and how that affects our gardening as urban, suburban, and even as rural farmers. So if you are a beginner at gardening, you really need to know what's going on with the earth beneath your feet, whether or not you're going to plant something up in a pot or whether or not it's okay to go ahead and put it directly into the ground. We're going to teach you some of those techniques about soil health and bring you some understanding of what soil really is. It's not just dirt, as people frequently call it. It's something very different. It's very vibrant, and it's an ecosystem unto itself. And if you take care of that ecosystem, it'll take care of you as an organic gardener.
Okay, so before we could jump into doing lab work and figuring out what's going on with the soils, we need to get a little theoretical background. And I don't want to take too much time with it, but it is a primer, and I'm going to assume that you have very little experience with soil science. So we're going to start with some real basics. We're going to take about 10 minutes, and then we're going to jump right into what you can do at home to assess the soil health for your own urban garden. Okay, first off, we need to learn what soil is. And first off, it's very clear that soil isn't just a bunch of rocks and minerals at your feet, but it's a system of material. It turns out soil on average is only about 50% mineral material, which means 50% of the rest of that space beneath your feet is something else. About 5% of that space down beneath your feet is organic material. This is dead and living microorganisms. It could be decaying material from plants and animals, and usually when you think of plants, usually thinking of tree roots, old leaves, things like this. In terms of animals, it could be a dead, a burrowing animal like a dead squirrel or something, but usually we're talking about dead springtails, nematodes, mites, protozoa, things like this. The remainder is pore space, which is taken up by air and water. So this is something that a lot of people are unaware of. The ground beneath your feet is more like a sponge than it is like a solid rock. Many people kind of analogize it to just being rock, and it's not that it can't absorb things, but it absolutely can. About 45% of the space is has space for air and water. So as a consequence, things can move through it. Living organisms, air, water, all kinds of things. So soil is teeming with bacteria, algae, fungi, protists, and provides habitat for earthworms, insects, mammals, reptiles, and amphibians. And since soil is composed of interacting living and non-living material, it is considered an ecosystem. So soil in and of itself is a giant ecosystem, whether it's the mushrooms or the ants or the ground beetles. And in complicated ways, they're actually interacting with the microfungi in the soil, including the fungi which is feeding on the nematode. So it's kind of an incredible situation. Now, soils are very diverse. There's a lot of differences in them. They change in color. They have different textures. The way that soils feel at the beach is very different than the way they feel in Chicago, for example. Structure of the soil, we're going to get into structure here in a little bit, and something called pH. pH is actually a measurement of the amount of hydrogen that is in the soil. And it turns out that's a big deal for plants. So soil color indicates the composition and fertility. So black and dark brown soils tend to have a lot of organic material. So if it's dark brown or black soil, you don't need to fertilize it probably a whole lot. It's already got its own built-in fertilizer. Where I live in north central Texas, there's something called the Blackland Prairie. In fact, that's the soil we'll be looking at for our own analysis. And it's a rich black soil with lots of organic material. And it doesn't really need any type of fertilizer at all. Pale gray or white soil indicates tremendous amounts of leaching. In other words, the weathering processes have removed many of those organic material, or much of that organic material from the soil. So it's not going to be as fertile as a black soil will be. Now, soil texture is determined by the size of the particles. These are those mineral material that we see inside the soil. And from smallest to largest, it ranges from what we call clay. Clay is slick and you can feel it. It can be sticky. Silt is something that you can feel. It's gritty, but you can't necessarily see it. You can feel it, but you can't see the individual grains. Sand, on the other hand, is something that you can both see and feel. We all know what sand feels like when we go to the beach or when we're at a sand dune. Probably the best of the soils for growing is something called a loam. A loam is a soil with an even mixture of the three. So an equal amount of clay, an equal amount of silt, and an equal amount of sand. Because it turns out that clay, silt, and sand all have certain benefits to a plant. But if you give it nothing but clay or nothing but silt or nothing but sand, it becomes difficult for the plant to survive. So it needs blends of these things, unless it's a especially evolved type of plant that can adjust to this. For example, things that live on beaches are really good at living on sand, but things that live in silt or clay cannot survive in those environments. Of course, the texture affects how easily air and water travel through the soil. Sand allows water to flush through very easily as well as air, but silt and clay less so, especially clay. It can be very restrictive. So you need to have enough clay where the water gets trapped in the soil, but enough sand where it doesn't waterlog and hold it in. The sand actually allows it to flow through. There's actually passage of water and air through it. And so we can characterize our soils based upon these textures. So something called something with 30% sand, 50% silt, and 20% clay can chart on a what we call a ternary plot. This is a three-pointed plot. Just like this. So sand would be 30%. So here's sand. 30% away from sand would be this line right here. 50% silt would be, see, here's the silt apex right here. So here's 50%. There should be a line dropping there. There it is. And then the 20%, here's the clay, and here's that 20% level. And they all cross right here between a silt loam and a loam. So this turns out is a very good soil for agriculture, it turns out. It's pretty common in the Midwestern United States. One of the most important nutrients that we need to worry about in soils is nitrogen. There are other ones that we have to worry about as well. Phosphorus and potassium are extremely important, calcium. But when most beginning farmers and gardeners start looking at soils, the first thing they lock in on is nitrogen. So nitrogen is pretty common on Earth. 78% of the atmosphere, it turns out, is nitrogen. Everything that you're breathing in, 3/4 of it is nitrogen. And it's in your proteins, it's in DNA, it's in RNA, it's all over the place. It's extremely important. But the problem is that nitrogen gas that we breathe in is not in a form that is usable by plants. It's also not in the form that's usable by us. It has to be changed. And the way that's done is through the nitrogen cycle. And it doesn't just show up magically into the plants. It actually has to take a path. So the nitrogen cycle describes the route that nitrogen atoms take through the environment, usually from the atmosphere, and then it gets deposited into the plant. And as we said here, nitrogen gas cannot be used by most organisms. So it has to be what we call fixed. Nitrogen fixation, which is done by lightning, or nitrogen fixing bacteria. These are bacteria whose whole job it is to do chemistry, is to convert gaseous nitrogen into another kind of nitrogen that is usable. So what they'll do is they'll take that nitrogen, they'll combine it with hydrogen to form something called ammonium. And ammonium, it can be, in fact, used by plants. That is suddenly something that can be absorbed as a nutrient. It's not favored by plants. Plants take on other types of nutrients better. So it turns out that there are also bacteria that turn it into those better forms. Bacteria then convert ammonium to nitrite, which is even more liked by plants than ammonium is, and then from nitrite to nitrate. Nitrates are what plants really like. So nitrate is the form most usable by plants. So it turns out that the amount of nitrogen that is available being produced by these bacteria limits the amount of growth plants can undertake. Plants will absorb every ounce of nitrogen that is in a usable form, whether it's nitrate or nitrite, as quickly as it possibly can. And so usually in good, clean, healthy soils, you won't see a whole lot of free nitrate or nitrite. They'll be in very small amounts. Okay, so that's an important thing to think about as we go forward with our experiments. Soils also have a structure to them, and these structures are determined by what we call their horizons. And it turns out there are many different structures that exist, but the layers that make up soils are pretty uniform. It turns out that each one of these horizons, which is a layer of soil, The typical soil can have up to 6 different horizons in them, and they're usually labeled O, which stands for organic, A, which is the top layer, the B layer, the C layer, and sometimes between A and B there's something called an eluviated layer, which goes by the letter E. Let's explain these here step by step, but we need to understand a couple of processes first. Now, the soil profile is the cross-section of the soil as a whole. Frequently, we just think about what's going on up here in the O and the A, but these things are down there as well, so we need to be aware of them. Leaching is a process whereby dissolved particles move down through the horizons and may end up in drinking water. So what falls here is going to wind up down here, and this is where the drinking water is eventually going to accumulate. So if you put a pollutant up here, it will wind up in your drinking water. Some materials in drinking water are very hazardous, not just naturally hazardous, but there are things that are artificially put there. For example, imagine a landfill, and it rains on that landfill. All that stuff goes right down into the groundwater. All right. Topsoil is the inorganic and organic material most nutritive for plants. This is what we're thinking of. It's the O and the A horizon up here at the top. And it's vital for agriculture. This is easily the most important part of the soil horizon. And this is where you'll be growing your plants if you're planting them directly into the earth. The O horizon has no mineral material. It's the very top layer up there. It's only made up of leaf litter and organic material. And it produces something called humus. Humus is a spongy material formed by partial decomposition of organic matter, and it holds moisture, so it's very valuable in that sense. Decaying organic matter creates humic and fulvic acid, which are important for plant growth. It also means that it's going to be raining acid. So once that rainwater hits the surface of the earth, it's going to go through the O horizon. That decaying material is going to put the humic and fulvic acid into it, which is going to change the pH. Remember, pH is a measure of the amount of acid or base in the soil. The A horizon is the layer right beneath it. So this is a layer of mineral soil with the most organic matter accumulation in soil life. So this is right up here at the top. It gets a lot of that organic material. It gets the mineral material. It's the richest part of the soil horizon. It's the most vital part of the soil horizon, and it's where almost all plant growth comes from. When we talk about topsoil, it's usually the A horizon that is so crucial. A lot of stuff also is removed from the A horizon, which winds up a little bit deeper down. A lot of oxides, like iron oxides, they can be formed and accumulated, but they can also be translated downward through something called the E horizon. So the E horizon is the next layer down. It's called the eluviated rather than the illuviated. So this eluviated means it's a zone of leaching. Remember, we got fulvic and humic acids as well as some other acids forming here, and eventually they'll build up and they'll change the pH such that you can leach all of the material or many of the materials that are down below right on out and transport it down. So right at the base of the A horizon, it's not uncommon to see this ghostly white layer that has all of those nutrients stripped out, all the organic material stripped out and transported downwards. Beneath the E horizon, you'll find a subsoil layer called the B horizon. This is right here. And this is where a lot of the minerals and organic matter that would have been up above will translate through the E horizon and then down into the B horizon. So here we have the A, the E, and the B right here. This is not a good zone for growing things in. It gets a lot of clay and iron and aluminum from up above. It tends to be a pink or red soil, and it's not something that plants really do well in. So it's best if you could protect the O and the A horizons up above, especially that A. And so to illustrate that point, I want to take a moment to show you a quick, field excursion that was taken by Dr. Friedland, who is a wonderful professor of environmental sciences, and one of his doctoral students from, I believe it was 2014, where they went out to go and look at these soil horizons so you can see the structures that we're talking about. It's very quick, and then on the other side of it, we're going to begin our own experiments that you can do at home.
So are the organic matter horizons really thick here?
They're very thick organic horizons, which allows for the development of spodosols.
Great. Will we get to see some sandy, leached E horizons?
Hopefully we should. These are very sandy soils and they allow for movement of water.
All right. So Justin, I was wondering, you never really told me, but how did you get interested in soils? What got you interested?
Soils are the connection between the non-living and the living world. So we have the rocks and minerals that provide the nutrients for the plants, and then we have plants and other organisms that live in the soil as a home. So it's this interaction between the biota and rocks and minerals that makes it a very fun medium to study.
And you're from California. Are the soils very different in California than in the northeastern U.S.?
So growing up in Southern California, we have very different soils. We have soils that lack a lot of the horizons. They have maybe an A horizon, a B horizon, but here we actually get to see horizons like the organic horizon, and we see the E horizon, and very, very red B horizon. So that makes it very special, something that you don't see in the rest of the United States.
Wow, that's great. So you've been to the site. I haven't. What are we going to see? What are we going to see here?
So we should see some very beautiful spodosols here. These soils haven't been disturbed, so they have very deep organic horizons. We should have very deep E horizons and very, very red B horizons. So they're very characteristic, very colorful, and some of the most beautiful soils you'll see in America.
So the path is just up the road here. Let's go take a look.
So right now we're in the Muskoma Highlands. We're just on the foothills of the White Mountain National Forest here in New Hampshire, which is along the Appalachian Mountains. And we're going to be digging here just north of some of these wetter areas so that we have the climates and the conditions for these spodosols. But we have deciduous and coniferous vegetation, and it's well drained, so the soils aren't soggy. They hold on to water long enough for the development of the spodosols. But they're not so well drained that we don't have horizon development.
Okay.
So it's a nice mix.
So they're oxidized soils. They're aerobic.
They're aerobic.
Decomposition going on.
Yes.
Okay. Great.
Absolutely.
All right. Should we go in and take a look? Dig
Yes,
some holes?
absolutely. Let's head
Sounds
this way.
good.
So this area looks actually very flat, undisturbed. It doesn't look like it's wet.
So like you were saying before, pretty well drained.
Yes.
Let's take a look around and find a place.
Yeah.
Yeah, do we want to pull that one? Now that we're not protecting that face, we can pull it closer? Yeah?
Yeah. Thanks.
So typically when you look at a soil, you have an A, a B, and a C horizon. The A being the topsoil, the B being the mineral soil, and the C being the unaltered material, much like the parent material. This is a very different soil. So Justin, tell us about this soil.
So here we have the typical spodosol, which is the state soil of Vermont and New Hampshire. It's characterized by this deep organic horizon. So how we characterize soil horizons is by the material that they're made of and what's been changing in each horizon. So here from the top we have this these leaves. So this is the
undecomposed leaves, essentially.
Next we have the accumulation of different types of organic matter. So here we can see some material that looks like wood, some decomposed wood. And we know that it's dominated by organic matter by actually feeling it and looking at it. So if you take a piece, it actually has a very greasy feel to it. Okay. Below that, we have the accumulation, we have the mineral soil. This leached, this white E horizon, E standing for eluviation. So where iron, organic matter, and aluminum is then leaching out of. So that leaves it with a ghost, very white color.
Okay.
Below that, we have the accumulation of organic matter. But this is no longer organic matter input directly from the leaves. We actually have decomposition and then translocation of organic matter from the organic horizon into the E horizon and then into the BH horizon.
Okay, so O, E, BH, and then?
So below this BH horizon, we have this orangey red horizon. So that's the accumulation and precipitation of aluminum and iron oxides. That gives it its red and orange color. So below this, we then lose the orange color and reddish colors to just a brown, a light tan, olive color. And that's from the unweathered parent material. So it hasn't had accumulations of any organic matter or iron oxides to give it any color.
Okay, so we've got an O, an E, a BH, a BS, and then lower B horizons. Is this your favorite soil?
So this is a very beautiful soil and is absolutely my favorite type of soil.
The spodosol, northeastern, north central United States.
Yes, absolutely.
All right, now that we've got our theory out of the way, let's move it out of the classroom and let's take it into the real world, into our actual gardens. In order to do that, we need to get a little bit of equipment. Some of the things that I need to get from the store are going to be things like coffee filters. Turns out coffee filters are extremely useful for analyzing soils. Aquarium test strips. You can actually buy them at any pet store. You go in there, the test strips are about $8. You get a tube of them. You want to make sure that they test for nitrates, nitrites, and pH if possible. And then in addition to that, strangely enough, one of the most useful things for analyzing soils, if you are a home gardener and you're interested in the soil pH, you need to get a head of purple cabbage. And I much prefer the organic variety to any other type, not just for the ecological reasons, but because you get a truer result. So make sure that you have those things and head off to the store. I'm actually going to head out right now, and when we come back, we'll have those items, and we're going to jump right into the lab experience of cheaply analyzing the health of our own soils. All right, so now that we're back from the store, we're ready to set up our home soil lab. This shouldn't be too difficult to do. I've got the things that I need. I've got my coffee filters right here. I got my aquarium test strips right here. And of course, I got my head of cabbage. In addition, some really helpful things to have from most people's homes is to have some mason jars. Most home gardeners already have these for canning, making jellies, and storing jams. Some purified water. Now, if you have really well filtered water, that's a good thing, but sometimes purified or distilled water, but this is usually something that you have in the house anyway, so some distilled water is really helpful because you want to have clean water to do your experiments with. And of course, some funnels. If you have some funnels, you can get that from any store, a couple of dollars, but I've got 3 different sizes here to accommodate just some fun soil experiments that we could do and to demonstrate some principles here. And of course, if you're doing any type of spring home gardening, you need to make sure you have a nice tall glass of ice water with you to enjoy the day. It's a beautiful day today. Here we are in late March 2021, and it is beautiful weather here in Central Texas. Okay, so the first step in doing any type of soil stuff at your house is to be able to get some soil. I've actually dug some out of my backyard here. I happen to live in an area where we have a soil type called the beautiful blackland prairie. It's a mollisol, which is a grass soil or a grassland soil. It's got a beautiful black color, which is where it gets its name from. It's one of the most productive soils in the world, but it's also very cohesive. You can see I'm holding the soil, and while little bits of it break off or whatever, it tends to be really clayey. It holds together. Water doesn't move through it really easily. So in order for me to do any type of soil analysis using water, I'm going to have to get this into one of these jars here, break this up, and so I'm going to see if I can break some chunks off. You'll realize there's roots, and occasionally you'll see bugs and worms in there. I usually try to let those out. And then what you do is you break it up, you put it into the jar, and you want to make sure that you use that distilled water or have that distilled water handy. So you can take this jar, fill it about halfway, roughly about halfway. Okay, and we're basically going to simulate what would come out of this in a rainstorm by adding some water, this distilled water. So I'd take this water and I'd fill it up. And one of the things I recognize here is this is very cool. This is very different than a sand, for example. A sand, the water would just come through and the sand would swirl around almost like what you would see on the beach. This is holding together pretty well. The clays are very cohesive. They stick everything together. And so if there's any sand or silt in there, I have to loosen that up. And so what I'm going to do is I'm going to take this and I'm going to add the lid, and I'm just going to shake this jar as much as possible to try to break that stuff up. And hopefully I'm going to liberate any of the organic compounds in there, any of the nutrients that are in there, and get that to dissolve into the water, because the water is ultimately what I'm going to be testing. So it looks like I'm actually doing a pretty good job. That stuff is breaking up really nice. I have a lot of root material and woody material that seems to be floating up and out to the top. Okay. So you don't have to do it too much, but you just want to make sure you get enough of it. In my case, it's going to turn into this almost like a chocolate milk color. Depending on the soil that you have, it might be a different color. If you have a lot of oxides, it's going to come up red. All right, so that's good. Now what we're going to do is we're going to take another clean mason jar, and in this case we're going to take our funnel. We'll use this size funnel over here, and then we're going to use the coffee filter paper. And the reason why we use the coffee filter paper is because we don't want that dirt material going down into the jar. We want to get a nice, relatively clean sample, and in this case, probably best to fold it over. So stick it here in the funnel. Sometimes the back of the truck doesn't always cooperate if you don't have a nice flat surface. So I'll see if I can make that work. Here we go. And then what you do is you open up the other jar and you basically dump it into the filter paper, like so. Now you want to make sure it doesn't come out of the funnel. It seems like it's working its way through. And what we're going to do is we're going to let this water work its way through. There's a lot of clay in there, so it's going to take some time for that water to drip on through that filter paper and collect into this jar. In fact, it hasn't even started dripping through yet, so it's going to take a little bit of time. Go ahead and be prepared to put that kind of time in. And if need be, if the clay is too much, in this case this is very clayey soil, if the clay is too much, you might actually have to do the filtration straight into the dirty water. But I usually prefer to do it through the clean filter paper if possible. Hopefully it'll cooperate and we'll get some good filtrate. All right, so hang in there and we'll be right back. Okay, so we're back, and I've actually been kind of fussing with this soil that I've got here in my sample jar. This Blackland Prairie stuff, turns out it has a lot of clay in it, and it kept gumming up the filter paper. One of the ways that you get around that is actually by putting in a cotton ball into the bottom of your filter, as opposed to using the traditional coffee filter. The problem with the cotton ball is it doesn't get all the stuff out, but another alternative is we could just go ahead and just use exactly what we have, that dirty water that came through. We could actually do our chemical test strip directly into that. So that's what we're going to do. So I actually have this here. This is the dirty water. Hopefully you were able to do it and get clean water by using the filter paper. But if you didn't, you can do it this way too. This is not going to give you nearly as accurate a result, but you can get a ballpark idea of what's going on. And so in this case, I've got my aquarium test strips. I've got a test strip already out right here. And in my case, I follow the instructions on it, and I'm going to put this in there for 2 seconds. And then you withdraw it. You see right away that there's some color changes that are happening on here. And I can then take my test strips, and I can compare it to what I am actually seeing on this diagram here, and I can get actual results. And so what I'll do is I'll show you what those results are here in a moment. Okay, so I've been able to review my test strip results, and I actually have pretty good results despite the fact I had to use that muddy, murky, clayey water. I actually can see pretty good values for what my nutrient levels are inside that soil. Another thing that we can do, and this is kind of a cool experiment, is to say, what would it look like if I was to add chemical fertilizer? This is a non-organic fertilizer that you can buy at almost any location. One of the primary ingredients that we have in here is something that provides nitrogen. In this case, it's ureal nitrogen and basically a version of ammonia. As we know, that those are both pretty common in the nitrogen fixation cycle. But this is actually designed to kind of bypass a lot of that and introduce it straight into the soil, that nitrogen. So let's see if it actually does put nitrogen into the water. What we're going to do is we're going to take another funnel, another coffee filter, okay, and then we're going to open this up here, and we're going to see what comes out of this particular brand of fertilizer. And the fertilizer, of course, is going to be a nitrate macronutrient, right? Or as well as possibly some nitrite. So we're going to see if that's going to show up. So we're going to go ahead and put that in our funnel and fill the funnel about halfway. Oh, it looks like it's spilling a little bit. And then what we're going to do is we're going to take that distilled water. Remember, this is clean water, so we're not introducing any type of airs into it, or very few if possible. And we're going to pour that over. And we're getting actually pretty good filtration, in fact, in this case. So, before the clays were blocking it, but this time the water is actually passing through the filter paper very nicely. It seems to be interacting nicely with the fertilizer here, and we should be able to get a pretty good sample to put a test strip in. And what we'll do is we'll look at the two test strips. This is just going to be fertilizer plus distilled water, and we'll compare that to what we get from the natural soil. Okay, so we've gone ahead and filtered that through, and we've got that filtrate right here. Very simple little process, just through the funnel. We're going to take another one of these test strips, just like we did before, no different. In my case, it's 2 seconds is what the manufacturer is asking for, so we put it in there for 2 seconds. We pull it out, and we start seeing instant color results on here. This is actually pretty impressive. So we're going to take a few minutes, we're going to let this dry out, and then we're going to compare the results of these two different test strips to each other and see what we get. Okay?
All right, so we have our chemical results, and we want to cover these really quickly and do a little interpretation. So we put in our aquarium test strips into the water, and we can actually see some interesting results. The column all the way to the left is what we got from putting it directly into the dirty water that is taken from the Blackland Prairie, which is my native soil from my garden. The second column from the left, the one in the middle, in fact, is the one coming from the fertilizer test strip. So this is where we took the fertilizer and we just dumped it. We put distilled water over it, and we put the strip into it. The third column is the series of comparable results. So we have at the top row nitrate, then nitrite, total hardness, total alkalinity, and then pH down at the bottom. The ones that we're going to concentrate on for the most part in here is going to be nitrate, nitrite, and total hardness. We're getting some really interesting results there. Turns out pH is not reliable for this test, and we'll get into that here in a moment. So for nitrate, all the way on the left test strip where we got out of the garden, the Blackland Prairie has almost no nitrate in it. So no naturally occurring nitrate. And that suggests that a very vibrant ecosystem is stripping that very valued and very important nitrate out and directing it into the plants that are in the environment. On the other hand, the fertilizer is got a very hot pink color to it, showing that it's that there's a lot of nitrate coming out of that water and into the system. When we compare that on the strip over to the right, we notice that it puts nitrate into what we call the harmful zone. It's the harmful level. So this is not a very good level of nitrate that is being produced by this fertilizer. Remember, these are ecosystems, and effectively nitrate, while it might be good for the plants, it's bad for literally everything else in that ecosystem. So once you start fertilizing things and killing off all the ecosystem services that are taking care of those plants, you wind up having to fertilize it year in and year out until the system flushes itself and corrects itself, which could take quite a bit of time. Organic farmers are familiar with the idea that it takes 3 years to flush this out. The next row down is nitrites. All the way to the left, and in the fertilizer column, in both those two columns, there's no nitrite. It shows that the fertilizer itself is completely nitrate in its origin, at least for what we can measure here. And for our garden variety, the nitrite, just for the same reason that the nitrate is being stripped out almost instantly by the local native population of plants. And then, of course, the bottom row is pH. The problem that we have with this pH is that we know that the soils here are not acidic, even though it lists it as about 5.5 to 6. The reason why it lists this is because the water that comes out of that water bottle has a pH of about 5.5, and it's dominating this. So what we did was we went out and did a second test to verify that it is not in fact acidic, that the soils themselves are actually alkaline in nature, and we're going to show you the results of that test when we pull out our head of cabbage and we make cabbage juice out of it, and we show you how cabbage juice can determine whether or not you have alkaline or acidic soils. So I hope that this was helpful. If you have any questions about it, please post it in the comments section. So there's one more very simple experiment that anybody that is interested in soils, especially in an urban environment, should be looking at, and that is the texture. And the texture can be figured out by looking at how clumpy it is, but another textural aspect is figuring out how much soil or how much clay, sand, silt
the soil has in it. And those have an important dynamics for figuring out how well water flushes through it, how well it holds nutrients, how the cation exchange capacity will function with the roots, and so on and so forth. So what I've done is I've actually collected 2 soil samples. One is my traditional blackland prairie, including that really clayey stuff that's really hard to break up. I put that in this jar over here. This jar over here is actually material that I collected from the road literally right behind me. This is a new construction road that is engineered. It usually has a little bit more sand in it. That's intentionally put in by the engineers when they build the roads for reasons kind of beyond the scope of this little discussion. But for gardening purposes, it gives us a good thing to compare things to. And so what you do is you take these jars, and I've actually already started the experiment, but what you do is you take these jars, you fill them halfway with soil, and then you fill them up all the way with water. And then what you do is you shake them up until there's nothing in there that's clumped together. Even the clays are broken up. And so that took me quite some doing, in fact, here in the blackland soils that we have here, because there's a tremendous amount of clay that's evident in it. This one over here was a lot easier to break up. So I shook them up, and then what you do is you wait, you set them down, and then you watch them for 1 minute. After 1 minute, you take a pencil or you take a photograph and you come over here and you mark them. Or you actually record the level of where the sediment inside the jar has filled up to after you've done a really violent shaking of that sediment. And in that 1 minute, pretty much anything that is sand size will settle out. And so you can measure that off. That tells you how much sand is in that sediment. And then what you do is you wait beyond that another hour. So it takes about an hour for the silts, and those will all settle out. And so right now I've actually got the sand phase done. I'm waiting on the silts to settle out. And then once I've got that, I wait 24 hours. And the clays should all, in theory, settle out at that point. So what we're going to do is we're going to run this experiment for 24 hours. I've already got my sand reading already off of these. I'm going to get my silt reading here probably in about 30 minutes. And then after that, I will have my clay reading sometime mid-morning tomorrow. So it's a very easy experiment to do. And then what I could do is I can come out and I could measure where those levels are. And if they're roughly equal, then I know that I'm looking at some kind of loam. If they're mostly sands or mostly silts or mostly clays, that'll make themselves evident. In fact, I did the clayey stuff over here, the clumpy stuff that I was doing in my experiments earlier, and there's almost no sand in it at all. So it'll be interesting to see how much silt and clay that I have in it. All right, so we'll check out what that experiment tells us tomorrow. So we've gone ahead and waited the 24 hours, and we've let our samples settle out. Over here we've got our sample from the road. Remember, the road is actually an engineered soil, so the engineers have intentionally put sand into it. Over here is our native soil that I actually collected from my garden from my backyard. The engineered soil, sure enough, has about 40% sand in it, about 50% silt, and roughly 10% clay. We could actually ballpark it between 5 and 10% clay. But this is largely a silt with sand in it. When we characterize that, that comes up as something called a silty loam. So it's pretty standard for what we see in engineered road construction. Over here, instead, we see something different. This has not been affected with sand. In fact, there's no sand in it at all. When we set the test up, we expected to see something. Nothing actually dropped out. Over the next hour, roughly 90% of it settled out as silt, and then we spent the next 24 hours settling out the clay fraction. So this is roughly 90% silt, 90 to 95% silt, in fact, and about 5% clay. So that makes it clearly on a little different portion of the ternary diagram that we showed in the lecture portion. That makes this going to be what I would classify as a silt. This is a pretty clear silt. But it doesn't take a whole lot of clay to make a difference. We kept calling it clayey. I actually meant that in the sense of a textural clay. Just a little bit of clay will actually make your soil stick together and be cohesive. It doesn't take much. Those little clay particles will coat around and stick to the silt particles in your sediment. So here I've got a silt that's pretty cohesive. There's just enough clay in there. And then this is going to be a silty loam that we see over here. In terms of the clays that we see in Texas, it's kind of important to keep these things in mind. The clay variety we have out here tends to be a swelling clay or swelling mineral. And what happens is when water gets into it, the crystal structure of the clay actually expands. And then when the temperatures rise out here and there's less water, the water is removed and the clays contract, which is why you get deep cracks in the summertime in the soils around here. So just wanted to share that information with you. For your gardening out here in the Blackland, this is what you're going to get. Now, where you're at, you would settle it out, and hopefully you would get something very silty with some sand and some clay components in it. That's great for growing. If it tends to have a lot of sand, be prepared to have to water it quite a bit. That means it's going to be a lot of drainage coming through. All right, so that's it for our texture experiment. Let's move on to the next experiment.
Let's get our pH indicator out of this purple cabbage. So this is sometimes called purple cabbage or sometimes called red cabbage. But the reason why we're using purple cabbage, and it has to be purple, not green, is because this is an amazing vegetable. It serves both as a pH indicator as well as being full of an enzyme called catalase. So it's actually used in a lot of different science experiments. But we're using it for its pH indicating properties. So we have to get the juice out of this thing. We happen to be using organic because that's what we use for vegetables at our house. So what I need to do is get about half of the cabbage. So I'm just going to cut half a cabbage here, and I might cut it into chunks just to make it easier to process in the food processor. Okay, so I have half my cabbage here. I'm going to just cut it up a little more, maybe into eighths or so. Be careful when you're using a knife, obviously. I also have here a glass of just filtered water from the filter on my fridge. We want, anytime you're doing sciencey stuff like this, it's better to use filtered water or bottled water because you don't want any minerals that are already present in your tap water to possibly interfere with your results. I also have an empty glass that I'm going to use to filter out the juice from the solids once we actually get that done. So ideally you would use some cheesecloth to filter it. I don't have any cheesecloth, so you could use a t-shirt, or I'm going to try using a coffee filter and see if that works as well. So I just have my trusty food processor here. If you didn't have a food processor, you could use a mortar and pestle like I have here, or any other creative way you can come up with to pound this cabbage to literally a pulp. So we're going to put the cabbage in here. In terms of how much water you need, there's no exact amount because it kind of depends on how juicy your cabbage is. So I'm going to initially try to chop this up without the water and see if I get enough juice that way. What you don't want to do is use too much water because it's going to dilute the potency of your juice. So I'm going to put this on, and initially I'm just going to pulse it. And then on high, just let it go. Okay, so all in all, I used the whole amount of water I had, which is about a half of a tall glass, so maybe about 8 ounces or so. All right, so let's see how it is. Good. So I don't know if the camera can see this, but it's nice and juicy and pulpy. You want the juice color to be really nice, rich, royal purple, like the color of the cabbage. So now I need to find some coffee filters, and I'm going ahead and I'm just going to lay those over the top of the glass and put the pulp into there and squeeze it to filter out the juice into the glass. Okay, so I have just a basic paper coffee filter here. I'm going to just kind of stuff it into my glass and put the edges over. And we'll see how much I can pour this without a spoon at first. So take the sharp part out, of course. And now we're just going to try to kind of guide this. It's get a little messy here. But I'm going to try to just squeeze some of this out. So you can see it's already filtering in there. And the idea is we're going to have to try to filter all of this in batches. So put this here, bring this up, and just kind of start squeezing it without letting the pulp get into the glass, because you don't want that in there. So as a pH indicator, this is a really fun substance to use, because what will happen is if whatever it is you're trying to test, in this case the soil, if it is alkaline or basic, it will turn green. If it's neutral, it will remain this dark purple color, and if it's acidic, it'll turn a beautiful hot pink fuchsia. So it's really interesting. So this will allow us to get rather a qualitative assessment of the pH of our soils. Okay, so we have a good amount of purple cabbage juice here. Now I'm going to set up just a little quick experiment just to show you the different colors that are produced depending on whether the solution you're testing is alkaline or basic, neutral or acidic, because soils can vary in terms of how acidic or basic they are. So I'm going to first just use some household kitchen stuff for our experiment. So for the basic solution, I'm just going to use some baking soda. And I'm just going to put in, a couple, maybe about a teaspoon and a half of baking soda, and maybe fill it halfway with water. These are just some little glass jelly jars. You can use anything you want, glasses or whatever, just adjust the ratios. Just going to mix it up. So now I have a solution that I know to be basic because baking soda is very basic or alkaline, has calcium, or it's calcium bicarbonate, right? So, sodium bicarbonate. With cabbage juice as a pH indicator, any kind of base should turn anywhere from blue to dark green depending on the strength of the base. Now, baking soda compared to something like Clorox mildew remover is going to be a much weaker base. So this should turn blue. So all I'm going to do is drop a little bit of cabbage juice in there. So as you can see, the cabbage juice correctly turned blue when in the presence of a weak base, the baking soda. So it turned it blue. So now let's, obviously if a solution is neutral, so for example, if we have just plain water, that should be a neutral solution. So if I just add some of the cabbage juice there, it should remain purple, which it does. And finally, let's check and make sure it's correctly indicating an acid. So I'm just going to use some organic apple cider vinegar here. You could use any kind of vinegar or any other acid you want to use. Just be careful. But this one is just found in your kitchen, so I'm going to fill this about halfway. Now this might give a slightly less hot pink just because it has apple pulp in it, but let's see what it does. So, ooh. So you can see how an acid, if our cabbage juice is being a pH indicator, will turn the acidic solution bright pink or kind of a fuchsia color. So there you go, acid, purple, or acid, neutral, and base. Okay, so now that we've tested our cabbage juice to make sure that it is in fact a pH indicator, so remember it turned acidic substance pink, neutral is purple, and a basic substance is anywhere from blue to green. So now we're ready to test the actual soil. So we have blackland prairie soil here, which is the best kind. And you can do this two ways. You can actually test the soil directly by putting the soil in a mason jar like this and pouring our cabbage juice onto it and letting it sit. And that will give you a ring at the top that you can analyze. But it's a little harder to see that way because the solids get in the way. So instead, what I would recommend is actually taking the soil, adding water to it, putting the cap on and just shaking it until you have a nice solution, and that's called a leachate. And then we're actually testing the liquid part of that, which is the leachate. So we've done this once already. We just put a little bit of the leachate into a small little jar like this and just added about an approximately same amount of, same volume of cabbage juice to it. So let's try this. So you can see I have just the leachate here. It's already started to settle out a little bit, which is good. I'm going to just pour approximately the same volume of our indicator into it. Give it a stir. Now again, there's so much solid still in this leachate that it's best if you let it sit. So the longer it sits, the bigger the band will be at the top of liquid that you can really use to see what the final pH result was. So to me, this has already kind of a bluish tint to it. Sometimes it also helps to add just a little bit of water, filtered water. That will, again, give you a bigger volume of liquid to solid. So I'm going to let that sit for a while. But, you know, cha-ching, like the cooking shows, we have a final product here. So you'll be able to see that the solids have filtered to the bottom or settled to the bottom, and The liquid part on the top is a clear blue color, indicating that our soil is basic. So there you go. Quick and easy grocery store test of the pH of your soils. Okay, so it's been about 5 minutes with the magic of video. And our sample we just did on camera here has been settling really nicely, producing a beautiful cobalt blue color. Clearly, these are alkaline soils. And if you can't tell just from looking here, we can actually do a simple little quick test to make the colors easier to see. So just little strips of paper towel. I'm going to dip it into our pure cabbage juice here. And that's, of course, that beautiful royal purple color. I'm going to lay it out here so it's easy to see. Let's test our most recent experiment that we did on camera of the blackland soil leachate. And we can see, holding that next to, a little leaf in there, next to the purple cabbage juice, clearly blue versus the original purple cabbage juice. Just to compare how time might affect it, this one was done about 30 minutes ago with the same soil. So you can see it's a darker blue because it's been sitting longer. Here's the one that was made with pure soil and not leachate, and it's been sitting about a half an hour. So again, beautiful purple color there, or sorry, blue color. And here's the one that I had done probably about 45 minutes ago. So let's check that one. And again, a really dark blue color. So the longer you let it sit to let the solids settle, the more, the deeper the color is for you to be able to tell exactly how alkaline it is. So this is all from the same soil, just done for different lengths of time and with different techniques. But in all cases, we can see that we have alkaline soil in our blackland prairie in my backyard versus the cabbage juice indicator.
Now we've just learned from our experiment using cabbages how to go ahead and make a pH indicator. And we've discovered that the blackland prairie where I live is alkaline, but where you live, it might be very different. So you need to make sure that you do the test to find out if you have alkaline or acidic soils. And if you have extremely acidic soils, it'll show up in that test. It'll be pretty clear because you'll get very bright colors. If that happens, it's always really in your best interest to contact the local office of the USDA, where they might have a soil expert that can help you grow the appropriate produce in your at your property, in your environment. What I have here are blueberries, blueberry bushes that are in pots. I actually cannot plant these into the ground here because it turns out blueberries don't grow well in alkaline soils. In fact, they don't grow at all. It kills them. So in order for these to survive and to produce fruit, I have to have them in pots and they have to be protected. If I wanted to grow something else, I have to make sure that it's going to survive in alkaline environments. So this is the reason why you find large swaths of the country growing certain kinds of produce and other parts of the country that can't grow it at all. So blueberries, for example, in Texas must be grown in pots. So these are organic blueberry bushes that we have here. Every single time I dig into the question of soils, I have such a great time and I learn something new. And I deeply appreciate you for sitting with us during this entire docu-lecture and learning about soils. If you have any questions or concerns, feel free to make a comment or to reach out to me. All the best. Just to show you, everybody likes soils. Never too late to start teaching kids about soils, even at a young age. Three, two, one. I'm gonna make an outtakes. It's some wacky cabbage.